In this lecture, we're going to go through parameter estimation and statistical modeling, which pretty much go hand in hand together. In many cases, we want to figure out a model to represent the data that we collect or the data that we simulate. Each time we use a model, it has to be made up of different parameters. And through parameter estimation, we can use our models and our data to find the best fit values for those parameters. So please keep in mind that this video will only give you a broad overview of these topics. Please look to the workbooks for a thorough discussion of each key topic, as well as different examples to work on. There will also be additional examples during the live lecture and also for assignment problems. So the goals in this chapter, number one, they're to understand the concepts behind parameter estimation, basically what it means, what different methods can we apply to do something like this. Number two, know how to generate a statistical model for a given problem using Python. So that would basically be trying to figure out what kind of model to use. Then we can apply programming knowledge to plot a best fit curve and determine its goodness of fit. So those are the three main goals for this chapter. We're going to split the chapter up into two sections, one specifically for parameter estimation over here at the top. So we'll go through what parameter estimation is, and then take a look specifically at maximum likelihood estimation, as well as its uses. I want to stress that when we're looking at maximum likelihood estimation, we're only focusing on the different steps involved. The course itself won't require you to calculate this from scratch, but will require you to know how to apply the steps through Python. The second section is broken up into linear regression. So that's going to mean taking a look at linear regression alone, higher order methods of regression, linear regression, and higher order regression analysis with Python as well. After that, we're just going to do a summary of the key concepts you should take from this lecture moving forward. Before moving on to the main content, I first want to go through an overview of parameter estimation, starting from first principles, and then take a look at different types of parameter estimation methods there are. Even though this course is only going to focus on maximum likelihood estimation, I do want everyone to know that that isn't the only way of estimating parameters. It's just the most common way of estimating things. So let's start our discussion of parameter estimation from estimation theory. So in the past, we were talking about inferential statistics. Estimation theory is now referred to a branch of statistics that deals with estimating the values of parameters based on our observed and measured data with some random component. So from estimation theory, it means we're going to be using the measured data that we have to estimate parameters that are a good fit for a model that we've chosen for our data. What is an estimator? An estimator is an attempt to approximate unknown parameters using the measurements we know of. So there are two general methods to approximate these values. There's two approaches basically. One is the probabilistic approach, which is highlighted in green over here. In this case, we're assuming that the measured data is random. So we have a random variable with measured data with a probability distribution based off of the key parameters. That's the most common way of taking a look at parameter estimation. There's another type of approach called the set membership approach. In this case, we're going to assume that we have a measured data vector and that vector belongs to a set that depends on a parameter vector. So that one is a little bit more complicated, so we are only going to be focusing on the probabilistic approach. So with all these definitions, we have to go back to the question of why is estimation theory important? So estimation theory allows us to take our sample of measured data as an input to produce an estimate or output of parameters with some level of confidence. So this allows us to infer the value of an unknown parameter in a statistical model in case we want to make predictions. It also helps to understand the behavior of a population with the help of a small sample size. So sometimes, and in many cases, you are not going to be able to take so much data. You can only grab so much data, and you'll have to make inferences about the population. So we can create a model to represent our data, go through estimation theory and predict the best fit parameters for our situation, and use that new model to predict behaviors within a larger population. So the question now is, how can we find these estimates and these values for our parameters? We have to use something called an estimator. So an estimator, the best analogy for this is what kind of rule can we apply, or what kind of function can we apply to give us an output from some input. So an estimator's definition is called some rule for calculating an estimate of a given parameter based on observed data. So our observed data is our input, and our estimate is going to be our output or our result. We're going to run our observed data through some rule, which is called the estimator, in order to give us a result from our quantity of interest, which is called the estimand. One of the most common ways of finding this estimate value is the maximum likelihood estimator method, or MLE. That's the one that we're going to focus on in this lecture. That's when we're trying to estimate the parameter of an assumed probability distribution given some observed data. What does all this mean? It means we are trying to, number one, use our observed data and find a probability distribution that fits that observed data the most. Once we have that, we can go through a process of maximizing a likelihood function for which that observed data is most probable for the distribution we've decided on. So we're going to be focusing on that for the rest of this lecture. Outside of this, I do want you to know that there exists other estimators as well. One of the most common ones is Bayes estimator. Bayes estimator basically helps to minimize the posterior expected value of a loss function. So what does all this mean? There's a lot of terms that we haven't really touched on before. First of all, I want to define what posterior is. Posterior distribution is a combination of a prior distribution, basically the distribution coming from your belief and your assumption of your values, plus your observed data. So it offers a little bit more accuracy because you're taking into account both the researcher's beliefs about the distribution and combining it with the observed data to get a posterior distribution. So then we're taking a look at a loss function. The loss function is going to be defined as the loss incurred in trying to estimate a value. So it's pretty obvious that we would want to try and reduce the amount of loss we have to increase the amount of accuracy that we have. So minimizing the loss makes sense, and minimizing the loss that comes from greater knowledge, which means the posterior distribution, makes it more accurate as well. So Bayes estimator helps us take a look at minimizing the loss function and error associated with our estimates. There's also another method, the method of least squares. This one you've probably heard of before. It's very typical in regression analysis. This is where we try to minimize the sum of squares of residuals to get the best fit for a set of data points. If you want to know what residuals are, it's simply the difference between your the model expected value and the value that you've observed for your data point. So the larger your residual, the less accurate your model is. The smaller the residual, the more accurate your model is. So with the method of least squares, you are trying to get a smaller value for the residuals to improve your accuracy. Finally, there's MCMC methods, which is defined as the Markov chain Monte Carlo method. We won't really be touching on this in this course, except in bonus material, but this is a class of algorithms to sample from a probability distribution. Once you have a bunch of values from your probability distribution, your algorithm can keep running until your Markov chain reaches some sort of equilibrium. Then you're going to take that equilibrium state and make predictions based off of that. So that is a huge part of machine learning and something that we can touch on in additional material for the course. So let's now focus on parameter estimation using maximum likelihood methods. I want to go through an MLE overview just so that everybody knows what it is moving forward, and then a step-by-step process of how to apply MLE. So first off, let's redefine MLE with proper terminology. MLE is a method that determines values for the parameters of a statistical model. For example, if we choose to use or apply a linear model to our system, then we're trying to figure out the best fit parameters for that model. So an MLE is going to help us answer this question. Which are the best parameters and coefficients for my model? So if we assume a linear model like we did before, up here, we can state the following. Y equals to, let's say, mx plus b. In this case, I'm going to use ax plus epsilon, where we have x being the input, y being the measurement or the output, a being the parameter in the model, given some postulated claim or error, epsilon, which is commonly referred to as noise as well. But no matter which model is chosen, whether it's linear, quadratic, exponential, or whatnot, we want to simplify things by using one term to represent our parameters. So that term or that variable is called theta. So we use theta to be a vector of all the parameters. With a linear model, we have two parameters that we're interested in, a and epsilon. So that means our theta is going to be defined as a vector of two values, a and epsilon. So then our goal with MLE is to select the parameters theta that help make our observed data most likely. So that means we have to make an assumption that the data we use to estimate the parameters are going to be independent as well as identically distributed, or else our modeling will become very messy. So based off of this, if we have our samples and our measurements given as x1, x2, up to xn for n measurements, then we assume that they are all independent and identically distributed and labeled as IID. So if we make that assumption, then that means that we can model each of these values based off of one singular distribution. And it's from that point we can start defining the likelihood of our situation. So first, we want to define what likelihood means. We've assumed that our data are IID, so remember what that definition means. So they have to share the same probability distribution. That's really, really important. And over here, I have the same PMF or PDF. We've already defined these before from previous chapters, but if you have a discrete function, then you're using a probability mass function. If you have a continuous function, then you're going to be taking a look at a probability density function. So you can only pick one of these, not both. And based off of your choice, you can then simplify things by using this notation, the function of x based off of your likelihood estimate, or theta for your parameters. And this means you have a shared distribution amongst all of your x values. So then what does likelihood mean and how is it different from probability? So first of all, likelihood refers to the joint probability of your data if it's discrete, or the joint probability density of your data if it's continuous. It means we're taking a look at the combined or total probability of everything. Since we have assumed that each data point is independent, the likelihood of all of our data can then be the product of the likelihood of each data point. So that means we're going to have to take a look at the product as a summation of all products. So mathematically, the likelihood of our data, given the parameters of theta, is defined as this. We have the likelihood of our parameters taking place being equal to the total product of all of our probabilities. So for different values of parameters, the likelihood of our data is going to be different. That's something that we can expect. If we have the correct parameters, then that means that our data will be much more probable than if we have incorrect parameters. That's why we write the likelihood as a function of our parameters theta. Once we have that likelihood function, we need to find a way to try and maximize it. So with MLE, we need to choose a value of theta that maximizes that L function. So we can use the notation theta hat to represent the best choice of values for our parameters or the best fit values. So statistically and mathematically, we can write this equation here, which defines theta hat as the maximum or the argument of the maxima of some function L. That argmax value is simply used to represent do something to find the maximum value of this likelihood. And whatever method you choose to find that maximum value is called argmax. So the argmax of a function is simply the value of the domain at which that function is maximized, however you want to find it. So why do we care about this? Because if we can find the log of a function, then we know that the log is a monotonic function, it means that whatever method we apply to find the maximum of a log will also be applicable to find the maximum of the likelihood function directly. So that means the argmax of the log of the likelihood function is the same as the argmax of the likelihood function. So that makes our math a lot more simpler because we can log the likelihood function and go through several steps to find the maximum likelihood parameters. So to make things simpler, we're just going to call the log likelihood LL like this. And we're going to set it equal to the argmax of the likelihood function L. So we have LL of theta being equal to the log of the likelihood function, which is equal to the log of this, which is the likelihood function. And if we take the log of everything, then we can simply sum it all up because this is a multiplication and sum of all the products. So we have the summation of the log of each individual distribution. So with this, the next step is simply to try and find the maximum value, which we'll go through in a bit. Okay, so let's try to estimate the best parameter values for a normal distribution. So we basically have access to n samples from our normal, which are our IID random variables. So we have the values x1, x2, x3, x4, so on and so forth until xn for n number of samples. We're going to assume that for all of I, xi is equal to some combination of values with a mean as well as some variance. So remember, mu has traditionally been used for mean in this course, and sigma squared refers to variance, sample variance. We're going to call theta 0 mu and theta 1 sigma squared, just so that we can have those two values as part of our parameters. So in order to figure out our MLE estimation for a normal distribution, we have 5 steps. Step number 1, we start off with the likelihood function. Step 2, we're going to assume that the normal distribution here is continuous, which it is. So based on this, we can apply the probability density function for a normal distribution given as follows. So we're just simply replacing this with the PDF function, which we've talked about in previous classes. Note the difference in the theta values here. Theta 1 is sigma squared, and we have theta 0 as our mean value. So we've simply replaced those two with theta 1 and theta 2. Now, step 3, because we're trying to find the argmax, or we're trying to maximize the likelihood function, and we know that it's easier to maximize the log likelihood, we first take the log of everything. So we're going to take the log of the likelihood function and end up with this. Now that we have this, we can rewrite it into an easier format like this. So based off of this new updated function, we can then choose values of theta that help to maximize it. So that means if you have multiple theta values, like theta 0 and theta 1, for your mean and your variance respectively, then it means we can simply calculate the partial derivative of the LL function and then set both of those equations to 0 and solve for the values of theta. This will result in equations for the values mu and sigma squared, which help to maximize our likelihood function. Typically, these two values are represented as follows. We have mu hat like this, and we have sigma squared hat like this. So you've probably seen these forms before, but we can run all of this through code to make things a lot easier. So overall, this is the method of normal MLE estimation, but there are also so many variations based on what distribution you're using. It doesn't have to be normal. It could be the Bernoulli or Poisson distribution. Whether you're trying to introduce noise or additional parameters into the system, and what you're trying to model. At the end of the day, you can either do this in a step-by-step old-fashioned way, like so, or you can run some Python code that helps speed up this process significantly. Now for the part that we've all been waiting for, how can we approach MLE with Python? So first of all, we have to import the required functions and packages, and that completely depends on what kind of data you're looking at, whether the distribution is exponential, normal, so on and so forth. So I'm going to leave that empty. Next, you're going to either collect or generate data. I have these two because sometimes you simply want to test your approach using dummy data, in which case you generate some dummy data and see if it fits well. In other cases, you're already given your data set and you have to find the best distribution to apply to that data set. So if you're interested in generating your own data set, you can apply something like this. So we're going to assume an exponential data set. It means for an exponential data set, you have to be able to determine your sample size. Let's say we want 100 values, and we want to determine some sort of rate because it is exponential data, so we need to know what the exponent is, and that's defined as 3 for the population rate. Then you're going to define some sort of exponential sampling size. So we call this the exponential sample. We use lambda to represent the parameter that we're interested in. You can call this theta as well. But it means that for every single n value that you have, you're going to calculate a random exponential value based off of your population rate for n number of samples that you're looking for. So this requires the exponential function from your random package in the NumPy directory. After this, you can define your sample overall. Your sample is equal to expon sample coming from this, or your sample size, which was defined as 100. So this purely means you've now defined sample as a list of all the different values that you have for your sample set. After you have your sample, whether it's generated or collected somewhere, we can jump through different steps with MLE. We already know the likelihood function has to be logged. And once you log something that is multiplied by each other, then you can simply add it all up. So that means we can define the log likelihood function directly without even defining the likelihood function. We're going to say log L is equal to lambda or theta, and we're going to define the rate as equal to something. So what this means is there are going to be some number of values in our rates, and that's going to be defined afterwards. I'll explain that in a bit. We define rates as the sum of all of our log functions. So we're basically using np.log and calculating the probability distribution for all of the different values within our sample based off of that equation that we had before. So I'm going to quickly go back to this equation over here. We're simply trying to mimic this equation through Python. So for every single theta or lambda value, we are calculating the log of the probability distribution function for our desired type of distribution. This was a normal distribution. Over here, I want to change things up and take a look at an exponential distribution to let you know this is where we would change things. So we're taking np.log of the exponential function, a probability density function, based off of however many samples you have with some sort of rate. Now, in order to figure out how many values of your log likelihood function you need, we're going to define rates as given by values from 1 to 8 with parameters of 0.01. We're then going to define estimates as our log L function of each rate that we're interested in. Based off of this, we can then determine what the best rate is to model our given data set or our generated data set. So from this estimates, we get an estimate of all of these R values for our exponential function. In order to find the best fit R value, we can use parameter value, which is just a variable name, rates, and then estimates.index to go through all of the different values in estimates, and then use the max function to calculate the maximum value for all of our estimates. So I'm going to reiterate this. We want to find the best fit parameter value for our distribution and our given data set. In order to do that, we're going to take a look at all the different rates that we've analyzed. We're going to take the estimates and turn it into an index to screen from. And then we're going to, from that list of estimates, determine the maximum value that is going to be our best fit. This parameter value can be plotted, and you end up with your values versus your parameter. And we see that the maximum value is given by a parameter of approximately 2.5. So essentially what this means is we've generated some data set, and we generated a data set based on a population rate of 3. Our estimation starts at step 3. We're trying to find the best fit parameter for the data set that we've created. It may not exactly be 3 because we are creating a random data set. So based off of our definition of how we log the likelihood function, as well as how we determine the best fit parameter, we end up with this curve, which tells us that for our data set, if we're trying to fit an exponential probability distribution to our data set, our best fit parameter is 2.5 or something along this line. Parameter value will give you the exact value, but even based off of the graph, I can tell that it'll be between 2 and 3. So that's about how we can approach MLE with Python using these steps. Just to reiterate, your estimation really starts at number 3 because you can either collect or generate data in step 2. So the second part of our chapter is linear regression, or basically regression. I am going to talk about linear regression specifically, and then take a look at coefficient of determination, and then general regression analysis with Python, not limited to linear regression. So what is linear regression? It is a linear approach for modeling the relationship between dependent and independent variables, and it's very commonly used for predictive analysis and modeling. So in most cases, we want to use a linear regression to search for a best fit line to a given data set. So let's assume our data set is xi and yi. We're basically interested in the parameters k and d that help minimize the sum of squared residuals, or some error called epsilon I. Please note that k and d are pretty much the slope and intercept of our y equals mx plus b function, and the residuals, epsilon I, will be the difference between the observed and predicted values. Because linear regression is solved to minimize the square of the sum of residuals, which we've kind of briefly talked about in the beginning of this chapter. It's commonly referred to as the ordinary least squares regression method. So please note that for linear and OLS regression, we can assume that all of the variability lies in the residuals, and that's where the entire analysis comes from. Based on those residuals, though, we can determine something else to help define the accuracy of our model, and that's the coefficient of determination, or R squared. So as a preamble, we don't just have to have a linear model. We can have higher order regressions based on what degree of function we're trying to fit. So we'll touch on this once we introduce some Python code, but we can have more than just a linear regression. We can have quadratic, exponential, and so on and so forth. But all of it doesn't matter if we don't know how to define the goodness of fit of that model. So that's why we have to introduce the coefficient of determination. So what is it? It's a statistical measure in a regression model that determines the proportion of variance in the dependent variable that's explained by the independent variable. This doesn't really help with the explanation, so we kind of have to look at the mathematical definition to figure out a better explanation for this. So we did say that regression is based off of a least squares method. Basically, we're trying to reduce the residuals. So with residuals, we commonly define it as the sum of squares, just so that we can see how large it can be. So it is the sum of squares by the proposed model divided by the sum of squares from all total, the total sum of squares. So we have R squared equals to 1 minus the sum of squares of the model divided by the sum of squares of the total. This tells us two different things. It tells us the relationship to unexplained variance, because R squared is going to tell us the variance of the model's errors compared to the data's total variance. It's also going to tell us the goodness of fit, because if we have a very small difference between the model's errors and the data's variance, it means that our model is very similar to our data set, and therefore R squared is optimized, and you have a much larger value of R squared. So 1 minus a very small ratio gives you a very large R squared value, which means you have a very good fit. In terms of the goodness of fit, when we're taking a look at what are the preferred values, that's extremely hard to answer. Keep in mind that if you are running theoretical simulations, or if you're taking a look at physical experiments, usually that goodness of fit, your R squared values are going to be higher than something from a biological nature, in which case we do expect fluctuations and therefore lower goodnesses of fit. So for the purposes of this course, I simply want to go through regression analysis with Python as the main component of regression analysis. In physics, we regularly take in observed data and we plot the points. After we plot the points, we want to be able to plot a best fit curve and then determine the parameters of best fit. So based on this, we can model it through Python code. The first step is the same as always. We're trying to import the required functions and packages. In this case, we're using NumPy, SciPyStats, as well as matplotlib.pyplot. So these three are the main ones. First, you can collect and or generate data. In this case, we're just going to take a look at a quadratic data set, which we can take a look at through the workbook. We're then going to plot the data points. So these blue dots are those data points. After this step, if we didn't have Python, we'd have to graph this manually and then determine all of the best fit parameters to model this curve. Otherwise, we can simply take a look at the blue dots and figure out what kind of curve to use, whether it's a linear curve or a quadratic curve or something of higher order. So depending on your choice, we then use a function called polyfit. So this polyfit function comes from NumPy, and it helps find the best fit parameters. So note that if you have an nth degree fit, you're going to need n plus 1 parameters. So if I have a second degree fit, I'm going to need 3 parameters for my best fit model. So based off of the blue dots alone, I personally think that we can just start with a quadratic analysis, which is a second degree best fit model. So that means because we have a second degree best fit model, we're going to need 3 different parameters. And that means we have to define the parameters as A, B, and C. Then you're going to set A, B, and C equal to np.polyfit. Call your x values, call your y values, and say that you're going to apply a second degree fit. So from this, we are going to get 3 values simultaneously that are saved as ABC for your best fit values. You're then going to define your model's equation, and that equation is basically ax squared plus bx plus c. So we have ax squared plus bx plus c. That's your new model. And then you can print out this model to get an entire equation so that it can be read by the viewer. Once you have that, you can plot the points of your best fit curve. Using your model, you can plot this model against your blue dots. So we can plot on the same graph your x values and y values with dots, which are represented in blue. We can also plot the x values and the model that we just defined here in orange as a best fit curve. We can then show it all and compare the two. And if we ever want an R2 score, we can find the R squared value using R2 underscore score from scikit-learn.metrics. So this last step is very important because in most cases, we do want to present an R squared value for our best fit model. So we define R squared or R2 as R2 underscore score of the X values we have, and then our model underscore quad to see how good it fits with our data set. So to summarize the whole lecture, let's take a look at what we learned about. First, we need to understand an overview of parameter estimation. You should be able to summarize different methods of estimation. Specifically, you should understand and apply the maximum likelihood estimation method. So be able to validate each step of the MLE method in case you're asked to explain why we're taking these steps. Be able to integrate the MLE method using Python to determine best fit parameters. And on the flip side, you want to be able to understand regression analysis and best fit models graphically. So be able to recite and analyze the steps for any type of regression analysis, be able to link the coefficient of determination to variance and goodness of fit, and then apply regression analysis techniques to predict the best fit models and parameters in Python. So that's about it for just parameter estimation and statistical modeling for the course. The next few chapters will focus on additional content that will be helpful in future classes, as well as data analysis in future projects.